Okay, today we continued our discussion of open channel flow, and we're going to focus on a case today where the slope of the bed, S naught, which is tangent of the angle also, is everywhere constant along our flow, and also the depth, y0, is constant, which means that as long as the flow rate is not variable in time, we have a constant velocity, v0. In this case, when we take our energy equation between 2 points, we know the pressure goes away. And so if you reference the video from our last lecture, this reduces to say that S naught times L, that's the slope of the bed, times distance between the 2 points. So L is the distance between points 1 and 2. Plus E1 is equal to E2 plus the friction slope times length, or the head loss. Now, if E1 and E2 are equal, as in this case, where they're both equal to y0 plus v0 squared over 2g, then those terms go away, and what we're left with is S naught is equal to the head loss per length. So how do we think about the head loss per length? Well, if we were in pipe flow, we could use the Darcy-Weisbach equation and write this as F times 1 over d v squared over 2g. Turns out that in pipe flow, well, I should say in general flows, we need to define a new parameter, the hydraulic radius. R sub h is going to be equal to the cross-sectional area of the flow divided by the perimeter. I developed this in more detail in lecture. And for a circular pipe, the pipe diameter is equal to 4 times RH. And so if we replace diameter with 4RH, then we can say that the channel slope is equal to F times 1 over 4RH, v squared over 2g. And solving this for velocity, we would have that velocity is equal to the square root of 8g over F times the channel times RH times the channel slope. And for wide rectangular channels, the hydraulic depth, I should note, for wide channels, the hydraulic depth is equal to the actual depth, y. Okay, now this form of the velocity tells us that the velocity is inverse with friction, as you'd expect. It's proportional to the channel slope to the 1/2. This is not the form that's usually used in channel flow, though. In channel flow, we go to the Manning equation. Now, in between Darcy-Weisbach and Manning equation, channel flow followed one other equation called the Chezy equation, but I'm not going to summarize that one here. The Manning equation is denoted as 1 over n times RH to the 2/3, channel slope to the 1/2, where n is now Manning's coefficient, or Manning's value. And this equation is specific for SI units. In English units, we would have 1.49 over n, RH to the 2/3, channel slope to the 1/2. Or in terms of the volumetric flow rate, we could write this as Q is equal to 1 over n times A, RH to the 5/3, channel slope to the 1/2. And for wide channels, or for rectangular channels, this becomes Q is 1 over n times the channel width times depth to the 5/3, channel slope to the 1/2. Now each of these, circle each of them, is variations on a theme, just different ways of writing Manning's equation. The main conceptual point for us to think about is that the depth that's defined by this equation, say circling it in blue, is a theoretical depth that would exist if infinitely uniform conditions existed. So if the channel was infinitely uniform both upstream and downstream, then it would achieve a depth given by this equation for a given flow rate, for a given Manning's n, for a given width, for a given slope. As we start talking about how channel flow evolves, whether the depth is greater than or less than this value becomes a critical descriptor of the flow, because it tells us whether the flow is gaining energy or losing energy. This is a topic we're going to take up in the next couple lectures. For now, though, let me just make sure that the definition is clear. This y is many times denoted as a subscript n and is the normal depth. So the normal depth is the depth that would occur if a channel was infinitely long and uniform.